Today we are going to discuss about the final lesson about our subject, which is about the current status of the deep learning, which would be a summary of the existing uh, technologies that are relevant to the deep learning and uh, everything that whatever we have discussed about the deep learning, how it was built, the process the scientists have come across, and how we have come to the status up to now. So, and we will be discussing the future implications of the deep learning and how the society would get changed and how what would be its economical and social changes that would be there in the future, both in short term and in long term. So first, let's look at the recap of deep learning, which we have where we have started after learning about machine learning. So we learned that the machine learning is about making decisions based on data uh, compared to the expert systems where the human judgments has to be encoded, right? So the machine learning was the key turning point which led to deep learning. Actually, deep learning is a form of machine learning, right? Uh, and in the earlier times of machine learning, before the deep learning era, it was mainly about getting some data set, especially the structured data. And then we feed the structured data into a machine learning algorithm, then train it, and then we can make predictions out of it. So which was far better than humans making decisions based on data, and it was basically uh, based on the statistics. That's why generally we call it as statistical machine learning. When it comes to the earlier development of machine learning, where it could be clearly explained with statistics, but later we found that with the development of internet and all the other IT related infrastructure and the social networks and all the other computer related uh, stuff that got popular throughout the past couple of decades. So it generated a lot of data, both structured and unstructured. So after getting this data, there were a requirement where if we could develop machine learning algorithms where we can improve our performance using this higher amount of data. But the existing machine learning algorithms based on uh, basic statistical learning could not achieve higher performance. Performance means basically the accuracy and precision, recall, etc. So that couldn't be improved with the number of data or scale the machine learning model or the number of parameters as required, as they were much fixed, where we have to uh, live with the amount of accuracy that was available, and by adding more data it didn't do much help. But the neural networks, which was inspired by the uh, biological neural networks, could scale well with the amount of data, where it could get higher and higher accuracy with the amount of data uh, that is available. So when you get a large amount of data, you can make a model that can make better predictions uh, than compared to the traditional statistical learning techniques. That is the reason why the deep learning networks or the deep neural networks got popular. But compared to the other machine learning systems, deep learning networks are highly flexible. Flexible means it can fit the data in a very complex way, which means it is highly prone to overfitting. In the other words, make in order to train a deep learning model, you need a lot of training computation power and also a lot of data to minimize the overfitting. But the plus side is that once you could successfully train a deep learning model, you can get higher performance compared to the other machine learning models. That is the uh, key difference the deep learning models took into the table. In order to reduce the overfitting, we had to come up with a lot of hyperparameter tuning, including uh, the regularization techniques like L1, L2, and dropout. So even after adding these regularization techniques, there were some other issues as well. For example, when we want to improve the power of the deep neural network, as we discussed, we have to uh, do it. We have to increase the number of neurons, but as we can't exponentially increase the number of neurons, which is not practical, we can increase the number of layers so that it can exponentially increase the power of the neural network. So as we learned, so we can, once we increase the depth of a neural network, it can exponentially increase its power. That means its representation power, uh, as it can represent a higher degree polynomial increased by one when you increase the number of layers by one. Right. So when you increase the number of layers, there were some other issues uh, coming into play. One of them was known as the vanishing gradient problem, and the other one is known as the exploding gradient problem. So when there are many number of layers, when the gradient is propagated from the last layer to the earlier layers, sometimes the gradient is getting reduced more and more, and it arrives zero. So in the later stages of the backpropagation, there would not be any gradient updates. That means the later later stages of the backpropagation can't do the learning process well. And so that is known as the vanishing gradient problem. So, and if the gradient is getting higher and higher exponentially, and at a certain point it exceeds the maximum limit allowed by this particular uh, variable size. That means, for example, if it is in certain variables can allow data in about 32 bits, some are allowing 64 bits, and they can only represent a certain number of numbers where it has a upper limit of the numbers that it can represent. And that particular number is saturated, it can't represent any higher number. So that is an overflow situation. So that happens when the backpropagation happens in later stages if the gradient is increasing exponentially. That is known as the exploding gradient problem. So in order to handle these problems, mainly for the vanishing gradient problems, the one way of using is using activation functions. So we discussed in the Rayleigh activation functions, it's always the gradient of the activation is always one, so it would not be increasing, which is causing exploding gradient problem, and it's not getting because it is not lesser than one, it won't cause the vanishing gradient problem. And when it comes to reducing the uh, increase of gradients with the number of layers, another alternative is to initialize the weight vectors. Although we can initialize in the random way, like which is known as the random initialization, still we can use some initialization techniques like HG initialization and so on, where you can reduce the probability of having the exploding gradient problem. So, and there's another technique known as gradient clipping, where you can clip the gradient when it is getting exceeded to a certain level. And also, in order to manage the numbers within a given range, we can use the batch normalization and layer normalization. And also, in order to overcome some of these problems, you can use the residual paths like we discussed in the ResNet, which can also avoid most of the uh, vanishing gradient problems. And now let's see how the uh, deep learning architecture was evolved from the very fundamental level of a neuron to the most complex technologies that we can see in today's world. So, like the other machine learning algorithms, deep learning neural deep learning algorithms are also based on independent variables known as X variables and dependent variables known as Y variables. So the smallest or the simplest unit of construction of a neural network is known as the neuron, which can be represented with basically a neuron where we have a weighted sum of uh, inputs and a activation function. So with logistic regression, we can represent that kind of a certain type of a neuron, right? So with the activation function, which is represented by the logistic function. And these logistic functions can can be used for binary classification. If it is a regression problem, you can simply use the linear regression. But if you want nonlinear outcomes, that is when we want to have logistic regressions, right? So when you have two outcomes, like two possible outputs, ones on zeros, that kind of output, then we can use logistic regression. And if there are more than one outcomes, more than two outputs, you can use softmax classifier as the output. So that is known as the multi-class classification. So these are the fundamentals of neural net. And if we want to have multiple Y variables, we can use several output neurons. So, and if you want to have uh, much to represent more, to represent uh, to have much learning capability, you can add the same features and have multiple weights by scaling the number of neurons, where you can have several number of neurons instead of a single neurons, where you can where each of the neuron can learn a separate number of separate features of the problem domain or the input data set. So that is known as a single layer perceptron, where you have several neurons in the which are operated in a parallel way. So that is known as a single layer perceptron. But in order to increase its computation power, you have to increase it linearly. So because that is not practical to increase it to a very higher dimension, you can increase its capability in the exponential way by adding multiple layers. So when you add multiple neuron layers, that is known as the multi-layer perceptron or a deep neural network. Right? So when you add a neural layer to a deep neural network, so it can increase its computation power exponentially. Right? And you can represent much complex structures with deeper neural network. So that, for example, uh, if you want to represent a face or something, the different layers are learning different uh, levels of structures. Like for example, the earliest layers near to close to the input layer would learn very basic structures like vertical edges, horizontal edges, and so on. And the next layer may be learning like vertical curves, horizontal curves, angled curves, and so on. The next layer would learn even complex structures like circles and closed loops, and so on. Another non-circular closed loops, ellipses, and so on. The next layer would learn even much complex structures like faces, eyes, and so on. So that is how each of the uh, neural layer can exponentially increase its understanding capability or the processing capability of a neural network by increasing its representation power with the number of layers. And also we have learned that when you have a deep neural network, you should always have uh, nonlinear activation functions for the neurons that are inside the neural network. So because otherwise it can be reduced to a single layer neural network, as we haven't proved, but that can be proved. So it can be reduced to a linear regression if you into a single neuron or multiple neurons if you are having only a linear activation function or not having a nonlinear activation function like sigmoid function or Rayleigh function. For the output layer, you can have either a nonlinear function like sigmoid function or uh, Rayleigh function, but and also you can use a regression function because when you want to have a regression output, you can use a regression function. You can use a linear function as the output layer, but for all the other layers, you have to use nonlinear activation functions. So as we found later, right? So we identified that Rayleigh activation functions or the rectified linear unit or its modified versions can be used in general for the activation functions for the neurons inside the neural network. So here I am talking about a multi-layer perceptron neural network. So there are much more different types of neural networks where we are not using rail, but there may be some other uh, specific versions of activations. So don't call it activations, but there are different ways to implement. But for multi-layer perceptron, this is how it is happened. And when it comes to the learning of a multi-layer perceptron, uh, as we discussed, first we have to find the error or the difference between the predicted output and the actual output is calculated. So it can be taken as the direct uh, absolute value of this difference or the square value. Both would be give a positive magnitude. Both would be give a positive value as the output, right? So in either case, you can use the that calculated error to backpropagate from the last layer until the initial layers are there, right? So what you have to do is you have to find how much each of the weights in each of the neurons has to be changed in each of the iteration, where you have to calculate how much each of the weights has to be changed for a particular error, like W by the bar theta, right? So sorry, the so we have to differentiate each of the uh, weight vectors, right? So you have to take this partial differential value from the end of the neural network to the beginning of the to each of the neural network, so which is done using the mathematically it is done as with the chain rule of calculus. Right? So once you take from the output layer to the input layer, you can calculate the uh, gradients that has to be changed uh, until the beginning of the neural network. So here, actually, we are not changing the exact gradients. So we are multiplying this possible change with the small scalar value known as the learning rate, right? So actually, we can change the learning rate with the uh, learning process. So there are certain algorithms like that, or there are some other optimizers that can use different learning rates with different parameters. Like most advanced one that is currently using is the ADAM optimizer, which is known as the ADAM optimizer. So this is used in general for backpropagation, right? So you may be using this kind ADAM optimization in most of the cases when you are using the backpropagation in neural networks. So when you apply the once you have calculated the gradients, you update the neural layers, neurons one by one. Uh, in a for a neurons in a particular layer, you can do it in parallel, but in order to go for the next layer in the backpropagation, you have to do it sequentially, because without calculating the values in the earlier layer, you can't calculate the next layer's gradients, right? So because of that, you have to uh, do the updates one by one in a sequential manner, right? And another advantage that you can get when you are training a neural network is using the transfer learning. Yeah, once you find that you have a generic data set, or so suppose something like that, so that if when you have a problem in your hand and you find that you have, but you don't have enough data, but for a similar problem or for a generic problem which is covering what your problem as well. If you have a huge data set, or you can download a huge data from the internet or somewhere, then you can use that huge data set to pre-train or the neural network where the earlier layers or the basic features can be learned with the transfer learning, where you can learn the last uh, or the most advanced features with your data set by freezing or using a smaller learning rate for the previous layers. So which is known as the transfer learning, where you transfer the knowledge that you have learned for the larger data set to to get the parameter values in the uh, of the lower structures of the neural network. So you only update the higher structures, one or two layers. You can update with your own data set, which is a smaller one. But because you have already trained the low level structures with the larger data set, now you can get higher performance with your small data set because you already know what are the lower level structures. Right? So that is the power of transfer learning. So this transfer learning is used for many other applications like we have discussed in with transform models. So we have so actually we can summarize the basically all the neural network architectures into two, like spatial architectures and temporal architectures. But this is not a very accurate one. But depending on our scope, about whatever we have learned, we can divide this into spatial and temporal. That means spatial means like which are like images, like data structures which has a very large number of uh, data points in a matrix, which is an image, and that can be considered as a spatial uh, problem, right? Spatial data, and when the data are given as a sequence, like the text or speech, where you have to uh, model the sequences that can be uh, called as the temporal uh, data. So how to learn spatial data and temporal data can be divided into two boxes, but there are certain ways that we can combine these two together, and we can have much higher dimensional learning systems as well, like three-dimensional uh, models, like the three-dimensional convolutional neural networks and so on. But in this case, just because we want to make the machines to learn about uh, the humans uh, visual capabilities and auditory capabilities, we can use the spatial and temporal capabilities as two different pathways of the neural networks, where we can use both of them to mimic the human being so that we can achieve the full level. So we can achieve the uh, final expectation of these neural networks, which is the AGI, artificial general intelligence, or artificial super intelligence, which we will be discussing somewhat later. Right? So, in the spatial uh, deep learning architectures, the first thing is the convolutional neural network. So, because the fully connected layers where the multi-layer perceptrons are connected to the next layer in the fully connected way. That means that all the neurons in the previous layer are connected to all the neurons in the next layer. So that is why these multi-layer perceptrons are known as fully connected layers. So these fully connected neural networks have some problems because when you increase the number of neurons, uh, the connections which are relevant to the weights are increasing exponentially. That is a problem when it comes to uh, processing very large number of input values, like for example, the pixel values of a image. So say for example, if you have 1000 by 1000 image, there are about 1 million pixels. So this is very, so there are 1 million input x variables. So that is very difficult to process with using a fully connected layer, because then you need like billions of parameters you have to maintain, and its computation power and the memory requirement is so high. It is not practical, and because there are less amount of data that you have to learn, so those are also prone to overfitting problems as well. So fully connected layers are not that suitable for uh, suitable directly to be used for uh, processing or the modeling image data. So we found that the convolutional neural networks can be done, because instead of using uh, fully connected layers for all the images in convolutional neural networks, we have convolutional layers where we have only a few filter which has a finite number of selected number of weights, and those weights are operated only on a small mask in the image for all the locations uh, of the image, which where we expect that the same pattern would be the same features would be repeated throughout the image, and that can be done in hierarchical way. That is the idea of using convolutional neural network. So we don't have to we only need to have a finite small number of weights uh, to apply, and because we don't have that much features and we have a lot of pixel and lot of mask values that you can find in a single image, so the overfitting would not be a problem as well. That is, and its computation is also not that difficult, and the memory requirement is also very uh, good compared to a full connected layer implementation. If you if you had to do it with for the full images, but in the later stages of the convolutional layers, we use fully connected layers after we have reduced the dimensionality of the uh, tensors that we after several layers of convolutional layers and max pooling layers, depending on your requirement, right? So sometimes we may have bottleneck, and then we increase the number of layers again to convolutional layers. So on. There can be different architecture, but in general, if you want something like image classification or something, later layers, final few stages can be uh, done with fully connected layers, because the dimensionality is reduced. But for the earlier layers, closer to the image input, we use convolutional layers where we can manage the number of inputs uh, using filters, right? And we have learned about the generative models with spatial architecture. The first thing we learned was the autoencoders, where which can generate, we can actually encode the internal structures of the image in an unsupervised way, right? So the CNNs or the convolutional neural networks can be used for classification and so on, but with supervised machine learning, where you need uh, labeled datasets. But in order to train a neural network in unsupervised way without any uh, labeled data, the best option is to use a supervised machine learning technique, something like a autoencoder, where it can internally identify the hidden features, the structure of an image, and can uh, train. It can extract the uh, this information in a bottleneck in the autoencoder. And in order to generate images from autoencoder, we can actually use, so in order to generate images uh, in a stochastic way, assuming it as a distribution, we can use variation autoencoders where we have, where we assume that the latent variables in the autoencoder are following a normal distribution, where we calculate the estimate the values for sigma and mu, where for the variance and uh, standard deviation and variance. Standard deviation and mean value. And from those values, then we can generate new images uh, using autoencoder, using a variation autoencoder. And we have also learned about the form of tuned autoencoder using known as beta variation autoencoder. And we have also learned about generative adversarial networks, which can also be used for generating new images in a very high quality way by using a learning process, which is a competition between two different neural networks. One is known as the generator and the other known as the discriminator. Right? So the generator neural network is trying to generate natural like images, and the discriminator is trying to distinguish the generator created fake images and the real images. So when those two neural networks are learning against each other, both of them are getting very powerful in general, and at the end, the generator wins, and the discriminator can't discriminate real from the generated images. So that is when you get a very high quality image generator using a generative adversarial network. Although this one is very successful at generating very high resolution, high quality images, there are some problems like uh, as it takes a lot of time and computation power to train a generative adversarial network due to its nature. Right? So instead of generating from scratch, from noise to images, we can divide this process into several steps by first adding images into noise in several steps and in the backwards, and that is known as a diffusion model. So with diffusion models, we can do stuff much easier and in a much less expensive way, in a much to generate images in a very successful way. So this is known as the denoising process, where you generate the images in step-by-step manner. And those are the stuff that we have learned about spatial deep learning architecture. So now let's look at the temporal deep learning architectures, mainly based on sequential models. Temporal means sequential, where we learn a sequence of events with the neural network architecture. The earliest and the simplest way of learning the temporal uh, patterns or the sequences was known as, with deep learning, is known as recurrent neural networks, so RNNs. And we found that although RNNs are simple, but they can't learn very long sequences, and they have the problems of this vanishing gradient problems and so on. Because of that, later people have invented long-term memory or LSTM and gated recurrent neural, known as the GRU. So mainly the LSTMs and GRUs are now used for, were later used for sequence data processing. And using these mainly if you are thinking about LSTMs, so using direct LSTMs in two directions, we can use bidirectional LSTMs. Where you can learn the bidirectional context of a sequence. That means you can learn from both of the directions and predict what should be there in the context. So it's like encoding the meaning of a sequence in two directions. So if it is a unidirectional thing, so you don't have to use, you shouldn't use bidirectional context, but use the unidirectional context where you should be using only a single directional LSTM sequence. And with in order to capture the much complex information, uh, that mean, for example, using not for example, so that is in order to represent the much complex information, you need to model them with much higher degree polynomials where you need much deeper neural networks, so you can have uh, somewhat deeper LSTM networks, but not that deep, but several, maybe 2, 3, 4, up to 8 layers, maybe. You can use deep neural networks or multi-layer LSTM networks, so you can learn these highly complex structures in the sequences as well. And later, people found that you not you the way the RNNs, LSTMs, and GRUs are working is using the sequential information given the priority, but so looking at how the humans are looking at sequential information where we give the attention only to some of them. The LSTMs with attention models were found and they were very successful. And later, the transform model was developed based on these attention models, where the attention for each of the attention is given only for some of the events uh, when the attention mask is computed first with transform models, and the sequence position, or in which position each of the event is located, is not given a higher priority, but it is encoded in sine and cosine waves, and it is added to the input known as the positional encoding. So that is how the transform models were developed. In the transform models, we have found that there are two types of two uh, main components known as the encoder and the decoder, where the encoder is encoding the sequence in the bidirectional context to a vector or two vectors, and the decoder is learning with the unidirectional context in autoregressive manner. So the advantage of transform is that it can be trained with language models which is an unsupervised learning technique, and then you can transfer learn it for whatever the task, something like with supervised machine learning, something like question answering, and then you can develop much complex systems like chatbots and some summarization engines and machine translators and so on using transform. And that is the idea. So when you train your transformer with a very large data set uh, with language modeling, that is known as a large language model, and so the trans initially learning with the large language model is known as pre-training a transformer. So once you have pre-trained transformer, you can use uh, the supervised machine learning for your task, which is known as the fine tuning. And later you can reinforcement learning for with human feedback or AI feedback for further uh, aligning with the human and organizational requirements. So that's all that what we have learned about deep learning up to now. And actually, there are some other techniques like Siamese networks and other uh, beam search and some and also for image segmentation, there are techniques known as uh, UNets, which we haven't discussed as well. And there are some other neural network forms like self-organizing maps and neural Turing machines, uh, which we have not discussed. And also, instead of using this multi-layer perceptron, there is a new uh, techniques that is getting somewhat popular, not popular, but was found that it is said to be working somewhat better, which is known as the Karmogov-Arnold networks. So, but those things, those techniques are not yet proven to be working for generic requirements, but maybe in future there would be better techniques more than the multi-layer perceptrons or the neuron abstractions that we are using up to now, which is a weighted sum of the inputs is then applied to a activation function. Though that is a very rough uh, approximation for a biological neuron. So that may get changed in the future, and it may have a big impact in the future of neural networks. Right, and there would be some other learning techniques competitive with backpropagation like Hebbian learning and voting and all those things, but we couldn't see that much popularity that was coming later in the deep learning community. But there may be some other techniques as well, like that may get popular in the future. So what I try to say is that this the structure of a neuron and the backpropagation algorithms are not the universal truths, but there can be. So though all of them are invented by humans, so they may find some better approximations or better solutions uh, for modeling the neurons to have better performance with less number of neurons and with much higher representative power. Right. So with the current emerging areas related to deep learning, stuff like that, like other than large language models, there are now large visual models where they can learn about videos and so on, where you can pre-train with data and then you can use uh, you can train it with your required task with supervised learning, and those things can be used uh, with the powers that we have received in the recent past using the large language models and diffusion models. And you can combine these two together and then you can achieve something really well. And the idea, the advantage of these models is that you can use unsupervised learning, where you don't need human labor to label the data, and it would avoid that the probability of uh, the human level accuracy, and you can exceed the human level accuracy when you are using the unsupervised learning. That is another advantage of using these LLMs and LVMs. There are, in order to uh, do multiple tasks, uh, now the techniques are getting developed to identify the common information that would solve most of the problems. Instead of solving a single problem, how to solve most of the problems in a single amount of meta information. So that is known as the meta learning. So where a model can be trained for multiple tasks, and once you learn for those tasks, you can train another task with a very few number of data, like the humans do, where humans are not learned for everything, but once they learn uh, with primitive stuff in the earlier childhood, now then they can do whatever with a small number of examples, uh, unlike the neural networks where you need thousands of data points. So, so the human is a good example for meta learning, where he can, when has learned for several tasks, he can do other tasks. So that is the emerging field of meta learning. And also for that is all for developing AIs. And in order to get the things done in the physical world, we need robots. So in order to make robots, we need reinforcement learning, where we want to control something depending on the environment and take actions depending on the inputs that we observe in the environment, and we have to adapt to the environment. So that is the uh, subject learning about the uh, reinforcement learning, where you can make robots and autonomous vehicles which can automate the human labor with autonomous learning, while the rest of the AI is based on replacing the cognitive labor, right? And also now these days, unlike the uh, humans did the Photoshop and other uh, techniques to and video editing and cinema graphics techniques to generate images and videos. Now with AI, you can easily generate images, and the writing is also very cheap because uh, LLMs can generate text very easily without human intervention. When you give the requirements and so on, the AIs can generate text and images and videos. And when can get text, we can generate speech as well. So those things can replace the human requirement for the industry. So that is another emerging field of AI. There are emerging fields of these tasks, right? It's not a single task. There are emerging fields in each of these domains. And when it comes to, although we have all these capabilities, when it comes to taking risky decisions like medical diagnostics and taking military decisions and taking decisions on economy, we have to be the humans have to take responsibility uh, about what the AI take, how the AI takes the decision. So we need some explanation or some observability inside the neural networks, at least to have some understanding how they are making decisions. So in order to understand how they are taking decisions and explaining it to the required authorities and the public is also a emerging field of the current AI development. So this explainability is one of the current uh, emerging field of related to legal and social uh, frameworks, where you have to convince the people what the AI is does and why it is reasonable compared to the existing systems, or without making a decision how this decision would impact, why it is good, and what is the probability, and all those things has to be explained instead of just saying this is how it happens. So, so those things are required in order to integrate the AI into our day-to-day life, because these decisions would be highly critical to the human life and assets of the economy. So the next, so the final or the main goal of the deep learning, as you may already know, that about it's about artificial general intelligence, where general intelligence means how we achieve the common knowledge or the common intelligence like which the humans have. So different organizations, different people have different definitions. Like in the earlier times, you might have heard about the Turing's definitions about artificial general intelligence, which is about the Turing test. But the Turing tests are now to all most of the many of the AI systems can now pass the Turing test. and there are now different ways people have tried to uh, up the bar of the AGI, and uh, s- because of that, people say still we haven't achieved the AGI in most of the cases, and but we have achieved the AGI in some ways. Like for example, if you write something in ChatGPT, you can if you were doing trying to do the same thing in the manual way, it would have take several hours, days, or even months to do the same generate same thing. But the ChatGPT can generate within several seconds. So that is another not artificial general intelligence, but it's a form of artificial super intelligence in that aspect. But when it comes to setting goals, taking strategies and long-term plans, or remembering the context of the task that you are working on, or with those aspects, the chat GPT is lagging. So those aspects, we are the these LLMs are lagging behind the AGI. So there are and also there are some aspects uh, like mathematical calculations and all those things. Some of the tasks where the AGI is lagging behind, where the LLMs are lagging behind humans. Uh, and those are some of the things that we say that we have not yet achieved AGI yet. However, we can see that there's a higher potential that we would achieve the AGI in recent future, hopefully, and we have to be prepared for that. And so once you achieve the AGI, some most experts say that that would be that would soon be converted into the ASI, which is the artificial super intelligence, where the AGI would would improve the AGI itself to write the code itself, or it's develop machine learning models for itself and update the models, generate synthesized data, and so on, so that it can efficiently increase its own uh, AI model so that it can achieve the ASI, artificial super intelligence, where it can exceed the intelligence level of human beings. So as the so ASI is introduced, it can also do the same kind of uh, AI development, and it can increase its capability in exponential way with the amount of data that is available in the internet and the power that you provide with the power grid compared to the power level that is there in our human brain, which is only limited to several dozens of watts, maybe several hundreds of watts, but it lot of power and lot of data, it can actually go to the artificial super intelligence very soon if the AGI is achieved, according to some of the experts. And so some experts say it would not be, but some say it would. Right? And and then for the in order to replace the humans, we can use the spatial and temporal models for replacing the visualization. For basically the basically replace the eyes and ears of a human brain, of a human, and we have the we all of them can be connected to the brain. Similarly, all the spatial and temporal models can be mapped into a uh, single vector space actually that is already there. So you can uh, create actually text or the sequential information from the spatial information, uh, which is like the generating the subtitles for movies, and you can generate visual information from the text information, where something like when you are creating a movie for a given uh, book or a movie script. So that is also possible these days. And also you can do the convert movies to video or images to another form, which is known as maybe video editing or some other transformation. And for the text also, you can convert one format of text to another format, obviously, like machine translation and text summarization. All those things are possible with the current AI, so it would take some time. It would not take a lot of time, in my personal opinion, to achieve the level of performance of AGI. So that's what's coming, and for that we may have to grab a lot of resources. So we should be discussing later in this lesson, right? And so what would be the applications of deep learning, like in the big picture, right? So the first thing is that the common deep learning models, the traditional ones which are using the structured data, would be replacing the existing computer-based systems and manual systems in business processes and uh, organizations. When it comes to unstructured data like images and texts, you can automate the knowledge workers or the knowledge human labor, where the scientists, engineers, doctors, and all the mathematicians and all the people have done up to now with their brains. Those people can be replaced with these deep learning techniques with unstructured data. And so what would be remaining for the rest of the labor force is the physical labor, so which can also be replaced with robots. The robot movements and the autonomous vehicle driving and all those things can be uh, done with reinforcement learning. So with the development of reinforcement learning, those things can be, this physical labor can be automated. So in order to develop deep learning systems in a scalable way, we have to identify what are the resources that are required for having deep learning systems. So talk. I have prepared this list based on the current requirements mainly required for LLMs, which is the most close uh, invention uh, to the AGI at the moment. So when it comes to LLMs, these are the resources that we need. We need high quality data. Like in the earlier times, we were using a lot of web script data, but later we found that the high quality data can get high output. So in the data science, you may always hear the term, hear the phrase garbage in, garbage out. And so in order to have a better model, you have to have better quality data to be trained. So you have to find how to scrape good data from the internet, or you have to find good data from other sources like books on so or any other available information sources uh, with high quality data. And you need a lot of computing processing power for tensor processing. So the currently that is those are done with tensor processing units from Google's and data processing units from NVIDIA. And there may be some other hardware based tensor processing systems that would be developed even with the analog systems. And so the current TPUs are working with digital data. So in order to reduce its power consumption and its complexity and the semiconductor usage, so that there is a new field of emerging. There is an emerging field that is researching about the using the analog neural networks for, and later we can use it for with quantization and so on to get the model after we have trained it. And so these models would be much cheaper and less power hungry compared to these digital models, where the human brains are actually an example of an analog neural network. So those things can also be developed with silicon chips as well. So that is another form of research. So and there are some other uh, digital and analog neural networks like examples are getting researched with optical data where the optical or the light signals are used as the electrical signals, replacing the electrical signals and replacing these neurons or the digital neurons. There are some chemicals that we can use to update the states of the neurons. So that is another field of research that is going on relevant to the deep neural network. So those things will also uh, may play a role maybe after some time, which would reduce the power consumption and other requirements related to the current systems related to digital processing and electricity-based computation. There are some much more advanced techniques are also getting introduced, like quantum computations, where you can reduce the uh, amount of computations significantly with in exponential way required for training machine learning models. So that is another field. So in here, what we are discussing is about the resources that are required with relevant to the current technology, right? And with current technology, we need a lot of power. Some say that it would need a lot of power, like terawatts of power. Some say it may need 10% of US current power consumption to train a very large model, right? So and the other thing is the required data scientists and data engineers for this training process. Although we would not be uh, in need of them in future, but in order to develop these uh, LLMs, they need a lot of uh, data analysts, data scientists, and engineers to identify this data and so on. And when it comes uh, to domain specific models, you need domain experts to uh, build these models, right? So those are the current uh, resource requirements according to the current technologies that are available with relevant to LLMs, basically. And in so when it comes to the large data deep learning system, so I'm not using the word large language models or something like that, because it may be mostly maybe with something with deep learning systems. So that is why I'm using large data learning systems, not language models. So language model would be maybe the most promising technology that we have at the moment, but it may be somewhat different in the future, but we don't know. So that's why I'm using the large data learning system. So with the development of these technologies, there would be uh, many concerns to the industry, to the society, economy, politics, and everything, technology and everything in the world. And so, because in order to, because there are a lot of debates going on in even in the expert community regarding the possibilities of these concerns. So I have taken the most reliable concerns as the short-term concerns, and the most controversial concepts into the long-term concerns, right? So which may happen. So which I personally believe, right? So the short-term concerns are the things that are where the researchers are working on at the moment, uh, which most of the experts are agreeing and they are working on them. The first thing is the ethical issues and biases involved with in decision making and training models with AI. For example, if you train a model for identifying terrorists or someone. So you identifying a certain Islamic group or something with images, classify them as terrorists. That's a religious based bias. And if you make a model to identify uh, thieves in with a CCTV camera, and if you try to identify them by their skin color, like the dark skin colored people as thieves, so that would be a very unfair bias in that system. So there are ways that you can eliminate the bias, or unbiasing ways that you can have to do it. And there are some other gender-based bias, age-biased bias, ethnicity bias, and many uh, inequalities that may be rising with the AI models, maybe depending on the data set, where they depending on the biases in the data set. So those things has to be handled as well. And those things are current research at the moment. And when it comes to training the models like LLMs and so on, and the large visual models, mainly the web data are used to train these models. The data extract scraped from the web, so there may be intellectual property rights violation cases as well, where the protected uh, images and text, or some artistic creation from very valuable resources may be used as the source for training these data sets. So they may generate the information that are modified versions of this copyrighted information or proprietary information. That would be an intellectual property violation case, and there would be a lot of uh, problems that would be having, or the concerns that they will face. So some say that it is something novel, because humans are also looking at the other people's creations, are creating their own stuff, and the AI is doing the same thing. But some creator says, "Oh no, it is not. So this image is almost the same as my one, which I have developed." And so then there would be a lot of debate going on with these intellectual property rights violations. And there would be similar privacy breaches by social network companies, where your photos or your personal behaviors may be used to train their data set, so that they can leverage your weaknesses. And maybe ad companies uh, can control or you manipulate your mindset uh, in a very uh, deep way. Even you won't understand, even you understand, you will not be able to resist, right? So even in the current advertisement systems, they do this, but with the AI based systems, they would do it in a very deep way, where you would not be able to escape in most of the cases. So that is a uh, very critical thing when it comes to the liberty, or the uh, of the public, or the freedom of their choice. So how do they select what they need if the ad companies are showing uh, or convincing them to do something that they would have done by their personal choices? So that would be another debate about our concern related to these AI systems. And when it comes to large language models, where you would need a lot of training, where they would need a lot of training, that would be a very big problem. sorry. And and when it comes to developing, uh, so there would be a lot of energy consumption when it comes to developing the AI models, where uh, that would need a lot of energy that would be used for the personal consumption, and for the consumption of the industry would be used for developing these large language models, which should not be used for the benefit of the society. It may be used for some other purposes like advertisements or military purposes, which would harm the uh, public as a whole. So that would be another ethical consideration with related to the usage of power in the uh, deep learning systems. And also when it comes to deep learning models making approvals or taking decisions, that would be a problem of transparency. For example, these days, United States drones can automatically identify the people's faces with the databases, and they can automatically fire the identified terrorists in Middle East countries. So that would be a problem if the decision is not taken by a human being and it is automatically taken by the AI. So that would be a problem uh, the about who has taken the decision and so on. So that would be another big problem. Uh, so that would be a problem when the machines are taking this decision. And also when the AI is taking decisions or doing some judgments, the humans can actually uh, breach these systems using the holes in machine learning algorithms, like something like using techniques like adversarial learning and its inherent deficiencies uh, and biases and errors. And all those things has to be identified previously, or they may not be transparent at the initial stages of the development. So we have to evaluate its possibilities when we are using the AI for very critical applications. So that is another concern. However, in the long term, it would be much scary. You may find, so this may be similar. This may be related to the things that you have seen in science fictions, like the AGI or artificial superintelligence uh, can affect the human existence in future. And the decisions that are taken by these systems, which would be very highly intelligent compared to human beings, would not be uh, possible for humans to evaluate whether we should approve these decisions to be implemented or not, right? So because we don't have the intelligence to approve their decisions, although they are taking the decisions under our supervision, that still that would be a problem for approval, right? And when they are taking decisions, we don't know their values, the whether these values are aligned with the human values or are they different, right? So if you are given a certain task like make paper clips to optimize the creating maximum number of paper clips, that doesn't mean you create you extract even the last blood of the all the human beings and extract the iron out of it and make the paper clips out of it, and extract all the mines in all the uh, soil in the world which contains iron oxide and make paper clips out of it. That's not what we mean, right? So So when you are given a target to a AI system, the AI system would actually make it may maybe taking it literally, that it would take decisions in a totally different way and to have a totally different value set compared to human beings taking decisions. So that would be a big problem if we find these kind of alignment issues with human value sets, right? And definitely when we replace the all the white collar jobs and blue collar jobs and worker jobs with AI, then there would be a huge income gap, wealth gap, and unemployment issue in the society, and there would be a huge economic uh, polarization between the countries who have the technology and who don't have the technology and the resources to do to run these technologies. So there would be a big power imbalance and economic instability among people. So how to identify, how to handle these things, so how these things would emerge, when, and how to handle them is a huge set of concerns that we have to decide. So those are the problems that we had up to now. So the list would go more and more. So I'm not going further. So I we can stop here. So if you have any questions, you can ask now.